Hey, everybody. My name is Dave Russell. I will be presenting today in the beginner track on a literally hands-on introduction to distributed systems concepts with Akka clustering. It's a long title, so I have to look at it each time I want to present. Okay, yeah, I said it right. I'm from Vancouver, British Columbia. Yeah, a lot of us made it out. So getting this across the border was probably hopefully the most exciting thing that happens today. We'll see how that goes. Right, so let's see. Is there anything else I need to do before we get started? I think we're pretty good. All right, so make sure you engage and review this presentation so I can get some good feedback on how I can improve the next time I bring 6 Raspberry Pis across the border and attach them to overly large balloons. That'll be good. Right, so ideally, this presentation is targeted to those of you who are just getting started with the concepts of distributed computing. Most of us have probably been working in a distributed environment for quite a while. If you are working on any sort of web front-end application that has a server on the back end. All right, so who am I? As I said, I'm Dave Russell. I'm on Twitter at DavidGreg. Greg is my middle name. My mom and dad gave me the most ubiquitous name in the world, so Greg. Yeah, I'm a developer at Hootsuite in Vancouver. I work on the Android application, and I write back-end services in Scala and Akka. What is Hootsuite? Hootsuite is the most widely used platform for managing social media. It's used by 10 million people. We have a web dashboard, an Android, and an iOS native app. What you can do, you can send messages, you can schedule messages, you can view incoming messages, and get analytics. So with all of that, we've grown a bunch over the last six years. Started up with this PHP application for speed. As soon as we started scaling that out, we're like, speed dropped. And so we started cutting away at this monolithic PHP application into microservices. But then the trade-off was that we got more services and more complexity around those services. So we got highly invested in cluster management and the ability to actually scale up and down these services. So here's the agenda for today. The first is the motivation. Why would you do this? And why would you use a distributed system? After that, we'll talk a little bit about some of the complexities that come into play when you decide on a distributed system and to start doing management of it. And then we'll also talk. Then we'll get right into Akka cluster and the ways that Akka cluster can solve those complexities for us. And then a demo. So the original presentation was going to have all of these sort of interspersed through the demo, but it turns out one of the complexities of running with a distributed system is that the network is unreliable. So I've got this 20-year-old router, this Linksys WRT. I don't even think it does like wireless N, it does G. So there won't be the demo will be held to the end, so we can get through most of the presentation. All right, so let's dive in. So the first question is like, why do I have a bunch of Raspberry Pis? Yeah, so there's a bunch of us at the company who were getting into reading white papers about Raft and cluster protocol, gossip protocols, and all these different topics in distributed systems. But there's this disconnect, this feeling like it's all really good, it's all out there, kind of nebulous. So the suggestion was, hey, let's just deploy all of our some samples onto these Raspberry Pis. They run the JVM, should be fine. So we did, and it's actually pretty great. It's an actual physical representation. You can start pulling wires, you can take bolt cutters and cut wires, you can hit stuff with baseball bats. I opted out of the baseball bat just because I wasn't sure if I'd let go of the bat or something really dumb, so we jumped over that. All right, so why a distributed system? Yeah, like I said, most of us are probably using it already, but from like a intentional perspective, you most likely are going to be moving from some application that you wrote quite quickly into something a little bit more scalable. The coordination of the services that come out of that become increasingly complex. Bitcoin uses a distributed consensus system to validate a Bitcoin miner to make sure that it's valid. And a specific use case, Hootsuite uses Akka cluster to manage connections to Twitter's stateful streaming API. We can reliably process 2 million users' data in real time. using Akka cluster. So it's a proven technology, works quite well. All right, so hopefully I've convinced you that you're either already using one or eventually will need to use one at some point. So let's talk about the complexities of a distributed system. Right, okay, the first one. The 8 fallacies of distributed system. How many people have actually have heard of this? Just at quick hands. Yes, half. That's enough that I can keep talking about it. All right. So the network is reliable. We'll just go over them really briefly. Most of them are pretty self-explanatory. I've starred the ones that I think Akka cluster actively helps with. I'm not so sure. I mean, it might help with that there is one administrator, but I'm not certain that that's the case. But from a concepts of distributed systems, these are fallacies that you need to make sure you're aware of when you're building your system. Each of them can bite you in a certain use case. Yeah, so those are them. I'm not going to go too deeply into them. Ideally, if you're starting to get into this, you'll read about them and architect your system accordingly. The far more interesting one to me, when I found about it, was CAP theorem. CAP theorem, it's an acronym CAP, consistency, availability, and partition tolerance. Consistency is the idea that all nodes see the same data at the same time. So you put a request onto the cluster, you should get a consistent result no matter which node is actually servicing that request. Availability is the idea that every time you put a request into the cluster, that you will get a timely response about whether the request succeeded or failed. And the last one is partition tolerance. A network partition is when you have a bunch of nodes in your cluster and there's like 3 of these here that can't talk to these 3 and these 2 can't talk to these 2, etc. And it becomes this idea of a split brain where you have 2 networks that are basically doing the exact same thing. And when you're working in clustering, that's almost never what you want. So in real life, it turns out that partition tolerance is not something that we have the option on. We have to deal with it. So the CAP theorem explicitly says it is impossible for a distributed computer system to simultaneously provide all 3 of the following guarantees. And like I said, in real life, it turns out you definitely have to take care of partition tolerance. So in the end, you really have to pick P, and you can pick consistency or availability. Which isn't to say that your entire system has to always pick one or the other. This is going to be a guiding principle that drives the design of your system, coupled with the nature of your data. So a quick example of how to see that this is an actual thing. Imagine you have some users on the East Coast and some users on the West Coast and some users on the East Coast over here. And the user on the West Coast, puts in a write into your system and says, hey, I want to write this state into the system. And so he writes it into this node, but before the data can get replicated over to the East Coast, there's a partition. So now you're left with this thing. Okay, so you've done partition tolerance, which means the system is still working. That's like great. But what happens to the guy on the East Coast? Am I still on my coast correctly? Anyway. The guy on the East Coast goes and requests that same state that the guy over there just put in. And so he gets it, and the system doesn't have that information. So your options are either to wait for the network to be healed, and then you can service this request from the guy over here, or you just give him the stale data, whatever was written over here at that time, and the user goes away with possibly incomplete information. All right, I think that covers CAP theorem pretty well. All right. Okay, so yeah, that was the first 2 sections of the presentation. The last one is basically like all of the things that we're going to talk about with Akka cluster. So this is the longest part of the section. Okay, so for those of you who are just beginning, Akka is a toolkit that wraps an actor model, which basically encapsulates some logical unit that then can pass messages to another actor over here. What it provides you is high-level concurrency, and it lends itself really well to distributed systems. So Akka remoting is a way to get an actor onto a different system so that you don't actually have to care where these actor systems are living. Akka cluster, is a membership service built on Akka remoting, and each actor system can be thought of as a node in the cluster. Nodes don't need to live in the same area at all. Akka cluster is going to help you manage all that. All right. So yeah, how do we pass information through the cluster? So we've got all these nodes that are in a cluster. How do you say move, you know, one bit of data to the rest of the node cluster? So the alternatives before gossip protocols were using Paxos, which was a strict consistency model, or you could use a centralized database to maintain your state. The problem with both of those is that they don't scale well. Database goes down, or you're spending a lot of infrastructure keeping that database alive, not your cluster that you actually care about. So yeah, gossip protocols come in pretty handy. What it gives you is a very resilient way of maintaining the cluster state. So yeah, you let each node hold the state of the cluster and tell your neighbors about it. Real briefly, let's have a look. Let's say you've got this cluster, they're the gray nodes, and then some external thing says, hey, let's write 7 into the cluster. So your first node receives the request. It needs to tell the rest of the cluster. So it randomly just picks 2 nodes and tells them about the change. Those 2 nodes tell some neighbors, and those neighbors tell neighbors, till eventually all of the nodes have seen the change in the cluster. And then you have something called convergence. Basically, when the last node has seen that all of the other nodes also have the same data, you can say that the cluster has converged. Akka cluster uses this state to make decisions for managing the cluster, and we'll get into that later on. All right. All right, so that sort of helps us with like intentional changes to the cluster. Like when a node comes in, we can gossip it. When we want to bring down a node for maintenance, we can get it out and we can gossip that. But this is sort of where rubber hits the road. How do we detect when a node fails when it's something that we didn't actually try to do? Without Akka cluster, you're looking at a third-party tool that would probably need to monitor each node in the cluster or have some sort of like outside sort of idea. Sensu would be an option, but that could be also cumbersome to scale. So Akka provides a failure detector. So each node, we'll get to that in a second, but like each node in the cluster runs a failure detector, and what it does is it will be monitoring its neighbors and keeping an eye on them. It sends heartbeat requests just to say, hey, are you up? And then you get a response back. So yeah, so you've got a bunch of nodes asking one node if they're up. If in Akka cluster, if any one of the nodes doesn't receive a response from the node that it's watching, it will alert the rest of the cluster that it is unreachable. The rest of the nodes won't actually actively be used, but they'll continue to send heartbeats to it. And so what'll happen is you'll get into 2 states. Either that node was, thrashing, or maybe a JVM garbage halting or something like that, or just a network partition. And you'll get either one of 2 things. Either it'll come back up and your node will be brought back into the cluster, or eventually, after a certain amount of time, Akka will actually quarantine that node and no more requests go to it. You'll actually have to bring that node all the way down and then add it back into the cluster later on. All right. So that's great. We've got a system that can detect when there's a failure, and we've got a system that can bring in and bring out a bunch of nodes. But who's making the decisions about like when the node can come in, what to do with a failed node? So this is the idea of a leader. But before we get that, we're going to hit that. We'll talk a little bit about cluster singletons. So this is a feature in Akka for when you need exactly one of something. Yeah. So the idea is if you've got one of your nodes running this role of, say, consuming messages off of a like a queue, and it goes down, you really need that functionality still. So it goes down, and another one will come up. Let's have a really quick look at that. This is pretty basic. So node A is acting as the singleton. Node A becomes unreachable. Node D becomes the singleton by virtue of being the second oldest member in the cluster. Singletons are always assigned to the oldest member. All right, so now we can go back to who's making the decisions. Let's talk about cluster leader. So cluster leader is essentially a singleton. And basically what happens is it manages this state. This is the state of the Akka cluster. So a node comes in and sets itself to be, it's in this joining state. And at convergence, the leader can move a node from joining to up. The node can then tell the cluster that it's leaving, and the node will then, or the leader will then move the node from leaving to exiting, exiting to removed. It'll just be gone. At the same time, if a node becomes unreachable through the failure detector, the leader will move this into a down state in sort of in a configurable way. We'll talk about that as well. All right, so let's just run through a quick example. So node F wants to join the cluster. So we have this idea of a seed node. You need to have one contact point, one way to get a new node into the system. It's not magic. So F currently is your seed node, or sorry, E is your seed node, and we're trying to get F in. So E then gossips out to the rest of the cluster. Eventually we have convergence, and the node F is moved into the up state. Now at this point, when there's convergence, what happens is you've got either could be a new well, F is now in. So the leader at this point, as far as leader election goes in the cluster, it is just whatever node is available to be the leader at that time. And the implementation is actually the first node in the sorted list of all of the nodes in the cluster. So the leader can change. And there is no actual formal election process like you'd see in a Raft protocol or something like that. All right, let's talk about handling partitions. This is sort of the big deal. If you were in the last session, there was some chatter briefly about cluster split brain resolver. We'll talk about that in just a second. A partition, like I said, is basically when part of the system can't see, or part of the cluster can't see the other part. So the 4 on the left there, or the right, are going to not be able to see the 2 on the left, and the ones on the left conversely cannot see the ones on the right. So there's kind of a few problems with this. One is that there's no real way for the system to determine whether those 4 nodes on the right have crashed, or if it's actually just like a network partition that eventually will come back up. There's no way to solve that problem. So what you can do is you basically say, how long am I willing to wait for those to come back before I do something? Because we can't just leave them there. Well, maybe you could, but we'll talk about that. So the first one that comes out of the box is an auto down. So the leader can just say, after a configured amount of time, just throw them out. Those 4 are not important. That works pretty well to get you started. But the problem with that is that what it leads to is those 4 still might be able to talk to each other. And so you have this split brain where those 4 are now acting independently of the other 2. If another partition happens, you'll see the same thing, and you can have these little islands of clusters, which is no good. So that's not a great cluster management strategy. The second one is human intervention using some sort of monitoring tool. You could say, oh, my network is having a hard time. I'll get in there and fix it myself. That's costly. It doesn't scale well. The third option is just leave the unreachable nodes alone. Maybe so when they're in an unreachable state, no new requests will be sent to them. They won't do any work. They'll just be hanging out. But the problem with that is that in Akka cluster, when you're in when one of your nodes is in an unreachable state, the leader can't make decisions. It can't bring new actors in. It can't down actors out. It can't do its job. So that's also not ideal. Singletons can't move around. Yeah, it's not great. There is a feature called actors weakly up that lets you to sort of get them in, but it's not quite enough. All right. So how do we deal with partitions? Yeah, so there's those two states. One is let's wait for some amount of time, and then the other is let's do something about this because we're kind of stuck. So the first thing I want to talk to you about is distributed data. It's an experimental feature in Akka 2.4. I've played around with it a little bit. We should be able to see it in the demo today. Basically what it is a merge-friendly, these merge-friendly data types. They're called CRDTs. They're like commutative, conflict-free, replicated, that's the R. Commutative replicated data types. They're also called conflict-free replicated data types. They're also called conflict-free. There's a bunch of the C's. There's a bunch of C's, but replicated data type is sort of the important part at the end. What it means is when your network heals, these data types will use some deterministic way to merge that data back in, so you don't actually have to go in and manually merge your data. All right, so that's that. We'll get into that later as well. And split brain resolver. I think this is like the big deal for Akka cluster. What it gives you is strategies to bring down some partition. So it acts on the last known state of your cluster. So some of the modes include quorum size. So you say, okay, well, we need this many nodes to keep up, so we'll just down the nodes that aren't inside the quorum size. There's a strategy called keep oldest. So wherever the oldest node is, we'll just down all the other nodes on the other partition. Keep majority, which is just like, okay, if there's 5 over here and the last known state of these two is that there's 5 over there, we'll down ourselves. And then there's a keep referee, was just like, okay, let's just have this one, whatever nodes are around this one, we'll keep this one, and that stuff will down. Some of the danger of that is that, like, if your referee is the only thing in the partition, then the rest of your cluster goes down, you have all the load on your referee. So things to think about. So a little bit of discrepancy right now. If you do, for some reason, want to use an experimental feature in your production, Akka 2.4, great. You can use distributed data. Split brain resolver is on 2.3 and is also part of the, you'll need a Lightband subscription to get that going. All right, let's do a demo. All right, so yeah. Let's keep going. So this was the original plan. We have a Wi-Fi router here. As I said, it's like 10 years old. So it's providing maybe 6 of you Wi-Fi access, which doesn't scale well, and the network is not very reliable. So I'm going to shortcut that by being the representative of the room. On my laptop is a web server running Akka HTTP, which will be servicing requests. Those requests will then be routed using a Akka remoting router in a round-robin fashion onto the cluster. Each node will service that request, and we'll see some stuff. All right. Ooh, too far. Spoiler. Okay. All right. So what I'm going to try to do here is I'm going to bring my terminal over. Can I do that? No, I got to bring down the stop presenting. Pause. There it is. Yeah. Oh, wrong screen. There we go. Let's bring that over. Cool. All right, so down here is our seed node. Ooh, too many. They're all my seed node. There we go. So all we're going to do here, I'm going to run a script that should bring up the seed node. So it takes a while for the JVM on a Raspberry Pi to load up. That's just, yeah, only Raspberry Pis, that's the only time. Yeah, so what we'll see here is that the member is up, and there's this internal scene changed event. What it means, it uses that to maintain convergence. So you'll see that flashing through the logs a little bit, but we'll keep going. So if I actually bring up my web server, just a second, just bringing SPT up. All right. See if I can bring that over as well. Yeah, I can. All right. So we're just going to run. We need the node that I am, which is 192. Is everything going okay with me? Yeah, okay. 222. And then we need to provide the node that it's actually going to be running on, which is Pi 2. Ooh, nice save, guys. Good work, team. Okay. No, 2 locals. That's not going to work. Guys, you didn't save the 2 Ls? Really? Too fast, you're right. Let's slow that right down. Code review. I don't think I need the, yeah. Oh, no, that should work. There. Let's hope. Oh, no. Huh, that's super interesting. Compilation failed. Value not found, current node mode. Oh, wow. Well, that's a bit of a downer. Let's see if we can fix it real quick. All right, so let's get into the code, which is actually where we're going to go anyway. So, Oh, that's totally why. Okay, I made some last minute adjustments. Who thinks that's a good idea? All right, so what I was going to do is show you a bunch of stuff about like, okay, let's do this first, and then we'll run through. So the code actually to get Akka cluster, sorry, I'm just dangling the demo in front of you guys. You can't leave till you go through all this. Okay, so I made some last minute adjustments, as you can see, of my Git history. Yeah, getting this all set up was actually remarkably easy. So what you do in your application configuration, you provide an actor provider at the top on line, looks like 3. Cluster actor ref provider. There's some required information from Akka remoting. You can provide the router here as well as where you'll route to. And then you're kind of off to the races from that perspective. There's a bunch of some other stuff that we'll do there. But the API app will need to revert all of my changes so that this will actually work. So we'll just eventually just revert those. Slowly but surely. This is what you guys came to see, right? Me reverting my code desperately on stage. Perfect. Perfect. All right. Let's see if it compiles now. Better. Oh, that's so much worse. Oh, boy. Let's have a look. Number format exception for input. Oh, OK, hang on. This is like exactly what I wanted. 192.168.222. That's true. Pi2.local. Okay. Sorry?
You have them in the wrong order.
Let's take a quick look. Shouldn't be too hard to figure out. Where are they? Oh, there. That's correct. Oh, there you go. Yeah, host is 0. OK. Whoops. No, the seed node should be second, right? So the host is correct. The args are acting as correct. Node's still up. Run. That should be, oh. No, the port's already there. Let's expect the same result. Well, that's going to be rough for our demo. However, let's take one more quick crack at it. What we can do is get the rest of the nodes working. So can we bring the lights down on the right a little bit? Is that possible? Is anyone running lights up there? No? All right, that's fine. Let's hope the LEDs that I bought were ultra bright. They should work. OK, so continuing on. All right, so we'll see how this goes. So this JVM will run up. Eventually, what you'll see if this lights up. Yeah. So I don't know if you can see this in the back. How good is the lighting? Can you see anything in these lights from the back? Yeah? Well, back left says good. Everyone else might need glasses if you can't see those. All right, so let's keep going. So what I'm going to show you as the nodes come up, we'll get the last one, and then we'll talk about it. All right, so what you see is these nodes starting to communicate as I bring the nodes up. What it is the gossip protocol chatting back and forth. We can talk about that for a little while. Bring that one up. And we'll bring that one up. OK, so what you're going to see as these go, the cluster receives a joining request. As that happens, what happens is the nodes start to gossip. Akka cluster uses a bit of a more complicated gossiping protocol than I went over in the slides. It's a push-pull protocol where one node will only send It'll send just the information that it knows about and sends that information out to the next node and says, hey, do you already have this state? If it doesn't, then there's a lot more communication between the two nodes to provide that state. All right. So as you'll see, so I'm using for this demo Akka cluster's auto down. It'll down after 30 seconds. So if any of these are sort of not working well, we should see that. In the other state, what we'll see is that the scene by should turn into 6 nodes all across the board, which it does. Yeah. The Akka HTTP would be great if I could get it to work, but it looks like that might not be an option for the demo. So what I'll do is probably sum up. So let's go back. Not that one. Back. There we go. All right. So yeah, we're gonna have to skip over the quiz. Actually, you know what? Let's just do it anyway because we're here. Okay, so yeah, Canada holds 20% of the world's. Put your hand up if you think it's maple syrup. Nobody. Oh, 2 people. Okay, good. Green, fresh water. Okay, and hockey players. Okay, I like the hockey players' answer myself. It's incorrect. Fresh water is the answer. So one of the things that you would see if the demo is working, we'll see if we can get it after the session. I'll let anyone who wants to get out of here go, but I'll keep playing with it for a little while after. What you would see is, yeah, so as the cluster goes through, as we start voting and we bring nodes up, the data starts getting replicated across the nodes, and you see this eventual consistency model that Akka cluster is quite good at. But as it stands, we won't be able to do that because the demo didn't quite go the way I wanted to. I should have named this presentation Tempting the Demo Gods. All right, so in summary, here's the things that we've learned. We've talked about why you might need a distributed system. We've talked about what complexities are added when you decide on a distributed system. And we've talked a little bit about the features of Akka cluster that will actually help immensely with managing that state. So thank you very much. Are there any questions? Yes.
Is that the code published on GitHub?
The code will be published it's actually published on Bitbucket right now, but I feel like it will be published on GitHub at GitHub/David Gregg. I'll also tweet that location. So yeah, if you guys spot that bug for the Akka HTTP, we could get a pull request going. Yes.
So in your dynamic environment, how do you maintain the IP address of the seed node?
I beg your, how do you dynamically keep track of the seed node?
I mean, how do you maintain the IP address of the seed node?
How do you maintain the IP address of the seed node?
Yeah, so say seed nodes are leaving, just like how can you run how the new seed node is registered to the class?
Oh, fair enough. So the question was, how do we know if the seed node is even in the cluster? Is that sort of the idea? Right. So it turns out that once your cluster is up and running, you can connect to any of the known IP addresses in the cluster. So you don't actually need the seed. You need the seed to start the cluster, but not to maintain. So at the same way, the failure detector would down that seed node. You'd know about it, and if you wanted a quick way to connect to it, you could actually bring that node back up and then connect to it as well. But you could do any of the other nodes in the system as well. Does that sort of answer your question?
Yeah, so if I want to dynamically join as unit seed node,
You need to know at least one IP address of the cluster. That's correct.
so normally what tools do you use for the resource discovery?
Sure. So currently we're using Console to maintain that list of nodes. Yeah, it works pretty well.
So I have a last question.
Yes.
So for the Akka cluster, you say the message is ghosted from node to node. So basically in Akka cluster, it is a complete graph or it's like a certain topology.
Oh, sorry. Could you repeat the question?
In Akka cluster, it is a complete graph or
A complete graph?
or it has certain topology.
In what way? How do you mean?
I mean, it's like completed graph is like every node connects to every node. So every node existence of other nodes.
Not exactly. So each node is responsible for knowing about a set of neighbors. So for example, in the failure detector, it's configurable, but out the box, it's five nodes. The way that it knows about those are when it registers at the beginning, it knows about what should be there, not necessarily what is up. Yeah.
So is there some sort of hinting if you've got your West Coast and East Coast stuff, you don't really want a whole lot of nodes to be talking across?
Yeah, absolutely. So there is the way that there is hinting inside the cluster specification in the documents talk about an opinionated gossip. So it tries to find nodes sort of in the same area that node is in. Does that answer, or does that?
Largely, yeah.
Okay. Any other questions? Yes.
Yeah, what causes a partition, and would you ever want to have one for any reason?
Other than for a great demo at Scala days? No. The question was, what causes a partition, and why would you, is there ever a reason to want one? The answer is almost universally no. What happens is you have, what could happen, so the demo, you know what, we can do it with the command line. It won't be as pretty as Raspberry Pis, and let's get back in here. Okay, so what you'll see here is that you've got all of the nodes have seen each other. So we have convergence, everything's working fine. What I'm going to do is I'm going to pull this red cord. Oh, I got really loud when I did that. And nobody's going to be able to see this, but keep watching. So I've pulled the cord between these two. I've got two routers, the wireless one and then the switch. So I pull one, and what you'll see is these two nodes are on their own on the switch, or on the router, and these four are off to themselves. So now we have basically a problem. You've got these four up here that can not see these two. And so what you're seeing is Akka cluster gossiping out, detecting a different state. So basically, yeah, like a physical accident. Somebody trips over a cord in a really poorly built network. A natural disaster could bring it down. A really bad, if you're running AWS, some bad deploys on the AWS side. I think there was recently an AWS issue. Yeah, let's see what happens. So if I get it in time. So I'm using auto downing. After 30 seconds, what it's going to do is automatically down those nodes, but I'll plug it back in and see if we can get the network running again. Let's see. The other thing is that my terminal sessions might be dead. But yeah, usually what happens is I'd pull it out. I wouldn't do the long explanation, plug it back into, Akka cluster will then go out and talk using the failure detector, go out and ping those nodes again, look for a heartbeat, and if they come back up, your network will get healed. Does that answer your question? Great. Any other questions? I think, okay. Yes? Is it possible to bring up instances dynamically? I missed the end part. Sorry? Only when it's needed. So you'd probably need a different tool to actually figure out how much load is on the cluster itself. But as far as that goes, Akka cluster, as far as I know, doesn't provide that functionality to auto scale nodes. You could use a third-party tool for that. Okay. Any other questions? Yes?
So you just kill your singleton right there, right? So I didn't see the nomination. Once the singletons queued up, you got to move to the other one, right?
This one? Yeah, so one of the things you're not seeing is this node here. So I've actually made the web server a node in the cluster. So what's happening is this is the sorted set. This is totally a guess. We'll have to you could look into the code for this. But the sorted set, I think, is just like literally, like this is 192.168.1.222. The rest are letters. So I'm guessing it's just the leader always picks this one when it can. So that's why you're not seeing it in this thing. I wonder if I could get the other one up. Oh no, because this is the answer. Oh wait, this isn't even in the cluster right now because it didn't work, did it? Yeah, that's a good point. So what you should see, let's scroll up in the logs. You should see like a leader changed. It's also in the you have to actually log this out to the console. So if I'm not logging it properly, you won't see it either. leader's moving node from here to somewhere else. So I'm not sure if that's the exact timing of that one. That looks high up. But like every time you move into a new convergence, so what'll happen is once you hit that partition, those two nodes will reach convergence, and the leader node may or may not move. There's a chance that it will or won't. That's sort of. Okay. Any other questions? Yes.
Monitoring this.
So at Hootsuite, we're using Sensu to do most of our monitoring. It's quite handy, yeah. PagerDuty to send out the alerts. Yeah. Yes.
So if I want to use this for load balancing, say I've got a bunch of worker nodes that are going to do things, and I want to have something that's receiving requests of some sort and dispatching out to whichever one happens to be handled. Do I have to build the load balancing myself, or is there something built in?
Yeah, for sure. So Akka Remoting has a bunch of routers that you can use, but there's a metrics extension that you can run in, I think, 2.4 that'll actually maintain, it'll retrieve metrics from your nodes to find out like what's under high load right now, and it will adaptively pick which node. It's really cool. It's a really cool feature in my opinion. Yeah.
That's only in 2.4?
I want to say it's an experimental feature. We should probably look into the docs for that. It's like right on the specification page. You can look right there. I don't want to give you bad information here. Okay. Any other questions? All right, guys. Thanks so much for coming.